We shall discuss memory organization today. As you are already aware, there are several kinds of memory like CPU registers, main memory, disk, etc. Each of these memories has its own characteristic. We shall discuss some relevant characteristics and properties today. Let us first come to the CPU registers. These are within the CPU, and therefore the advantage is the CPU can access it almost immediately when it needs data from it. The access time of these registers, that means data in these registers, is 1 to 3 nanosecond. Therefore, you can see that if you can keep your data within the CPU registers, the computations is very fast. Now, the number depends upon that how much is the packaging density of the chip. It has to fight its space for with the other elements within the CPU, and the number is from several dozens to several hundreds, okay, and width will depend upon the width of the CPU. It may be 16-bit, 32-bit or 64-bit as the CPU width is. Next come the main memory, and last of all we will discuss the disk. Now, when you come to the main memory, we call the main memory as a random access memory. We call it a random access memory because wherever the data is, to access the data, a constant time is needed. A constant time is needed, and therefore we call it a random access. Now, this random access memory consists of several cells. I have shown a cell here. Each cell can contain either a 1 or a 0. Okay. The several inputs to the cell are a select input which selects the cell, a control input telling that what to be done, either a read operation or a write operation. If it is a write operation, then there should be a data in. If it is a read operation, then there should be a data out or data sends. Now, a cell is essentially an electronic circuit. The exact construction of a cell is beyond the scope of this lecture, and therefore I will not discuss it. Only thing that we will talk about is that there can be static RAM and there can be a dynamic RAM. In the case of a static RAM, the information in the cell can be there as long as power is there. That means if a 1 is here, it remains until the power is made off. Okay, similarly, if 0 is there, it can keep 0 until the power is put off. Okay, that is why we call it a static RAM. In contrast to, there is another kind of RAM, we call it a dynamic RAM or DRAM, where if the 1 or 0 that we hold starts gradually wiping off. The reason I'm telling is this, that in the case of a static RAM, it's an interconnection of several active devices, making it a flip-flop, so to say. And in the case of dynamic RAM, that flip-flop contains either a 5 volt or a 0 volt. depending upon whether it is 1 or 0. I mean, when I say 5 volt, it's near 5 volt. When I say 0 volt, it is near 0 volt. But in the case of a dynamic RAM, 1 or 0 is represented by whether a charge is there in the capacitor or the charge is not there in the capacitor. As you know that if we charge a capacitor, the charge drains off, and therefore there is a tendency that one will gradually wipe off. That is why in the case of a dynamic RAM, we'll have to refresh that one, that means the charge, intermittently. Generally, it needs, say, refreshing between 1 millisecond to 4 millisecond, and for that there should be a circuitry which should recharge the cell when it is needed. Okay. Now let us see some of the characteristics of the static RAM as well as the dynamic RAM. Okay, and that access time in the case of a static RAM is lower. It is 5 to 25 nanoseconds, and in the case of a dynamic RAM, it is higher. It's 60 to 120 nanoseconds. Okay, therefore, from the access time point of view, naturally people should choose static RAM. If a bipolar technology used, the access time, that is the time to access a word, say from the RAM, is around 10 nanosecond. Okay. Space per cell is much more here because, as I said, that is interconnections of active devices, I mean the transistors. More or less 6 transistors are needed, whereas this needs only 1 transistor. And therefore, the space per cell is more in the case of a static RAM than in the dynamic RAM, 6 times more approximately in comparison to the dynamic RAM. So, the packaging density is less in the case of a static RAM, here it is more, and therefore, the number of bits that you can contain in a chip is much more in the case of a dynamic RAM than in the case of a static RAM. Cost per megabyte as stands now approximately is between $100 to $200, and it's $5 to $10 in the case of a dynamic RAM, and therefore you can see that cost is much less in the case of a dynamic RAM. Therefore, if you have to utilize a huge amount of memory, naturally people will use dynamic RAM. Nature is both of them are volatile. Okay, by that I mean if the power goes off, the information stored in these cells or the memories that are constituted out of these cells will all go. Okay, therefore the power has to be there, and that is why we call it volatile. Now let us see that a RAM organization consisting of such cells, right? Now, as we have seen while we are programming or utilizing computer, to us the memory that is presented by the computer, I mean the main memory that is presented to us, is a linear one. That means in one-dimensional one. We go, say, I should say that word by word in the memory in a linear fashion, right? If we look at this picture, it's a one-dimensional or 1D RAM. There is an address buffer where the address comes. Okay, let us assume that it's an M bit address. There is an address decoder. Okay, and for example, if there is M lines in the address, okay, there should be 2 to the power M outputs of the decoder. Okay, from A0 to A2 to the power M minus 1. For example, if it is 4, there should be 16 lines, right? These are drivers which drives it. Of course, depending upon a particular combinations of the address here, a particular line turns out to be active, and therefore the cells that are in one line being driven by the same address driver, okay, will be active. The data will be either read from the cell or will be written into the cell, okay, that comes over to here, the data buffer in the case of a read, and that goes out to the data bus, right? These are read-write drivers. That means in the case of a write, that data should come here, and on being selected, that particular address, all the cells in that word will be written into depending upon the data bits here. Now you can see that if we have to have a 1 mega word, okay, I am assuming that word is the minimum accessible unit. It may consist of several bytes, right? If we have a 1 mega word address, right, that means if we have 20 lines here, then we will require 2 to the power 20 address buffers at these points, right, which is a huge thing. 1 megabyte of address buffers and 1 megabyte of address lines, okay, into the memory unit, and therefore such a one-dimensional RAM is rarely used. In fact, it's not used, okay. But from the conceptual point of view, as we see, as a programmer, we see view the memory, so to say, looks like this, okay, as if we are going word by word arranged in a linear fashion, right. This is the one-dimensional organization of the RAM. Let us come to what we say that a two-dimensional or 2D organization of the RAM. Here what is done is this, that address bus, okay, so consists of M lines that comes over to here, is split into two parts, okay. One is of MX width, another is of MY width, okay. For example, if it is 20, it can be say 10, 10, or it can be say 12, 8, and so on, right. Now this comes into the, we call it row address buffer, and this comes into the column address buffer. The memory cell organization is like this. It is in two dimension, right. These are the rows and these are the columns, okay. Now the MX lines from row address buffer, we call is that X dimension, so to say. It comes into the row address decoder, and since the number of lines here is less, the number of amplifiers that is needed is much less, and the number of lines that is needed is also less. So is for the column address decoder. For a particular address, say the ith line will be high here or active here, the jth line will be active here, depending upon what is the value of MX and MY, and one particular cell within this memory cell array will be active, okay, which has been shown by means of the pink, right. Now, so to say, this is fully selected. Other cells here in these columns are half selected. Similarly, other cells here in this row is half selected. This particular ijth row is fully selected, which is sensed in the case of a read, so that data out or data in, this is our data, it's a 1-bit data, is either is read out or is written into, okay. Now you can see immediately in the case of a two-dimensional RAM, that number of lines here either from the row address decoder or for the column address decoder reduces, right. Now here is only 1 bit we are talking of because it's only one plane and one cell is active, okay. If you need that more bits over here, we'll have to have an organization something like this, okay, that instead of one cell being active, that when I and J turns out to be active, it activates in the same plane more than one cell simultaneously, say 8 cells simultaneously, then 8 lines can come out of it, which can come into the data buffer, and that 8 bit can emerge out of the data buffer, okay. Now, for example, this is an arrangement I am showing of a typical cell, which is 8 mega into 8 bit DRAM, right, okay, dynamic RAM. The organization that we are talking of here is applicable to both static RAM as well as dynamic RAM. Therefore, I am not mentioning whether it's a static RAM or the dynamic RAM. I am talking about the organizations only, right. In the here, so for example, that 8 bits can come here, therefore that 8 bit can be merged, right. Now, what in that this particular this particular chip, it is done this. MX is 13 bits, okay, split into 13 bits here. MY is 10 bits here, so that it is 23 bits here. The 23 bits is needed for 8 mega bit of addressing. Okay, 20 lines makes up 1 megabit. Okay, 1 mega, and therefore, if we have to go for 8 megabit, there should be 23 lines, right? Such an organizations we call 2.5D. It's not 3D because you know that we are not talking about a third dimension here. In 2 dimensions, we are activating 8 cells simultaneously to come to this 8 bit, right? This is our 2.5D organization. Now, if we want that, we'll have to go for example, utilizing this kind of arrangement, right? So, for example, we have a memory organization or a memory chip, which is 1 bit, okay, 8 megabit, okay. That means there's 20 lines here. Any one of these 1 megabit cell can be selected, and 1 bit information comes out of it, okay. If we have to use such 8 megabit cells to organize more memories, then let us see what organizations we can go for, right? This is a picture I have shown here. Say 4 mega into 8 bits, okay, which means 4 megabytes of memory I want to create, right? This is the address space that, okay, or the memory space that we are thinking of. Each this box is of 1 megabit, right? 1 megabyte, for example, B0, B1 to B7 are the 8 bits, data bits. The addressing is 20 bits is needed for this 1 mega addressing. That means from A0 to A19. These 20 bits will be needed to access any of the bytes in this memory portion. And so far as this total 1 megabit is concerned, right, we are putting 2 more address bits, A20, A21. For this one, A20 and A21 will be 00. For example, if it is 00, then it means that this 1 megabyte I am addressing. If it is 01, this means that this megabyte I am addressing, say this is 00, this is 01. Similarly, this should be 10 and this should be 11. Therefore, to address 4 megabyte of information, we will need 22 bits, A0 to A21, out of which up to A19 will give you 1 megabyte accessing, right, from all zeros to all ones here. This 00 will select, say, so to say, this portion, right? If this is 01, then say this portion will be selected. If this is 10, then this portion will be selected, and this is 11, then say this portion will be selected. Therefore, 22 bits we need. A20 or A21 will need to select either of these 4 portions of the memory, each one of which is 1 megabyte, and within that particular portion or within that particular block, A0 to A19 will select a particular byte within this memory block, right? Now let us see how this organization we can have from, say, a memory chip which is of this nature, okay, which gives 1 megabit of memory, right? Let us see first this portion, okay. This is the chip that we are talking of. we have A0 to A19 address lines. There is a particular input we call chip select input. This chip select, if it is active, only then this particular full chip is selected. Okay. Otherwise, the entire chip is inactive. There's two more controls. We call it write enable. That means if this is on, then a particular bit within this 1 megabit can be written into. And there is another control we call output enable. If this is on, then a particular cells whose address is A0 to A19, okay, is outputted into the output line, right? Therefore, this is write enable and this is output enable. There is a chip select which selects this chip. This has to be active. As I repeat that this has to be active if this particular chip has to be active. That means it can at all operate, right? Now what we can do is this, that the 21 address lines that we'll be needing for 4 megabyte, as I said, okay, the 20 and 21, the most high ordered bits of our address, okay, the most high ordered bit of our address, that means this 20 and 21, right, most high order bit of our address, we put into a decoder. This is a decoder, which means that if these two inputs is 0, 0, then this line is high. Sorry, this line is high. If it is 0, 1, then this line is high. If it is 1, 0, then this line is high. And if it is 1, 1, then this line is high, right? Now, say we first talk of how to make this 8-bit information out of this 1-bit information, right? What we do is this, we take several such chips and place in, I should say, parallel with each other. This is our, say, chip 0, this is chip 1, and so on. This is chip 7, right? Each one of them is selected. For example, this particular chip, okay, the chip 0 in this stack is selected by means of, say, this one, okay, chip select. That means if it is 0, 0, then this chip is selected. And when this is selected, you see all the planes, that means all the chips in this stack are all selected, right? This chip select line goes to all the chips in this stack, right? The other address lines from A0 to A19 is also parallelly fed to each of these planes, right? Each of these chip, okay? This goes here as well as here as well as here, which means for a particular address, okay, 22-bit address, depending upon A20, A21, which means if it is 0, 0, then the entire stack here is selected, and depending upon A0 to A19, one cell and the corresponding cell of each of these planes, that means each of these chips is selected, therefore making B0, B1 and B7 lines, okay, outputting, in the case of a read, the content of the corresponding cells in each of these planes or in each of these chips, right? Let me repeat what I'm saying, that depending upon A20 and A21, if it is 0, 0, then the entire stack is selected, right? Say I am reading. In that case, depending upon A0 to A19, one cell, okay, in the position, okay, in the same positions in each of these planes, that means each of these cells will be outputted through these lines. The first one will come to B0, second one will come to B1, and similarly the seventh one, that means the A, will come to, say, B7, right? This will now come to the address bus. See, now this will naturally make 1 megabyte from 1 megabit, okay? The address of this entire stack of cells, stack of memory, is A20, A2100. Now, if we now have to make 4 megabyte, okay, then we'll have to use 4 such stacks, okay, or 4 such planes of chips, right? So the chip array, memory array 0, memory array 1, memory array 2, and memory array 3, right? The chip select for all of them is 00, 820, 821, 00. Okay. For this one is 01. That means the entire 7 such chips will be selected when 820, 821 is 01, choosing our this megabyte. Okay. Similarly, 10 will choose this megabyte. Okay. And 11 will select, okay, this megabyte of information, right? Now, for this 4 megabyte of information, this one, this one, this one, and this one will be selected by A20, A21. Each byte in each memory array will be selected by A0 to A19, thus giving us a memory organization where we can have 8 bits, okay, or 1 byte, okay, output, and we can select any one address out of this 4 megabyte. Okay, this is therefore a memory organizations of 4 megabyte into 8 bits or 4 megabyte information that can be made out of this 2-dimensional RAM, which is a 1 megabit RAM. Okay, now let's see therefore how many such chips are needed to make it a 4 megabyte chip. Here it is 8, and each one of them will need 8 chips. Therefore, we will need 8 into 4, 32 1 megabit chips to make a 4 megabyte memory organization. Now, this is, I am showing as an example. Naturally, you can see that today's computer consists of several megabytes of main memory, okay, and therefore some such organization has to be adopted to realize it. Okay, this is so to say an example organization just to tell you that how from say lower order memory chips you can make, I should say, that higher order main memory. Okay. Now, let us see what are the different semiconductor memory types. We call it semiconductor memories because, you know, these RAMs also are semiconductor memories, because basically, as you know, that VLSI chips are consisting of semiconductors. We have talked about the RAM already, which is a read-write. This is volatile. The power, whether it is dynamic or static, doesn't matter. The power goes off, whatever the RAM contains also goes off. Now, there can be ROM, we call it read-only, okay. There can be ROM, the programmable ROM, that means we can program it, this read-only memory, program it once and then use it as a read-only memory. There can be EEPROM, that means erasable PROM. This erasing is done by means of ultraviolet ray. There is a window above this chip. If you put ultraviolet ray on this window, right, in that case, that whatever is written goes off, then you can electrically rewrite what you want, and then you can use it. Okay, and here it is EEPROM. It's electrically erasable PROM. Here we are using ultraviolet ray. Here that electrically whatever is written can be erased. This we can talk of is read mostly. This is, okay, program once and then read afterwards. Okay. Now, all from ROM to EEPROM are non-volatile, which means if the power goes off, the content remains. Okay. That is why it's called non-volatile. Now, these are so far as semiconductor memories are concerned. Let us now come to what the magnetic disk memory. Okay, the magnetic disk memory is somewhat like this, that there is a disk surface. Okay, it's a disk, it's a surface, it's a magnetic surface. It looks somewhat like this. For example, say this is a magnetic disk surface. Okay, now to write informations and to store informations here, this magnetic disk is divided into several what we call tracks, right? And each track is divided into, so to say, several sectors. This magnetic disk is rotated at high speed, okay, 60,600 RPM to 7,200 RPM, okay. At high speed, this magnetic disk is rotated. There is a head here like this. The head can move this way, right? Okay. And as it moves from one track to other track, the information can be written into track to track. Okay. For example, if it is here, then the information is being read into this track or written into this track. If it moves to the next one, then the information will be read or written into this track, right? Now, this magnetic disk, okay, for example, when you come to this magnetic disk, right, the both sides, that means the upper side as well as the below side, can be written, okay, which means that both sides are divided into tracks and each track is divided into sector. The advantage of magnetic disk, as you know, that we can contain a huge amount of memory, okay. We call it, so to say, that external memory, because for the CPU to access some data into a disk, okay, that's kept in a disk, an input-output interface, okay, separate input-output interface is needed, okay, to access data from a disk, right? In that, when a separate input-output interface is needed, we call it an external memory. Okay, in contrast to the main memory of the CPU registers, we call it internal memory, because the CPU can directly access an information in the CPU registers or the main memory. A separate I/O interface chip is not necessary. Okay, that is why it's called an internal memory. Now let us come to that when it's kept it this way, that you will have to read a particular. If you have to read a particular data from a disk, then one complete sector has to be read out from here, or if you want to read a data into the disk, one particular sector has to be written into, which means that minimal accessible unit in the case of a disk is a sector, right? Even if you need, say, for example, few bytes, the entire sector has to be read out, or if you have to write, say, few bytes into a particular disk, that the entire sector has to be written into, okay? Now let us see that in the case of a magnetic disk, what can be the further situation. The magnetic disk, here I am talking about the hard disk and not the floppy disk, so to say, that it can consist of several such magnetic disks, okay, arranged. It can be around 10 such disks arranged on a spindle. The spindle is rotating at a very high speed, okay, and there are read-write heads for both the upper surface as well as the lower surface of a disk plate, right? This is a platter. There can be 10 such platters, as I said. This is rotating, and if you have to move from track to track in a platter, okay, naturally this head assembly has to move, okay, so that a head can move this way or that way. Now the track, okay, in each surface, the lower and upper and lower of each platter or each disk, okay, constitute one cylinder. That means if this is the track number I, then the track number I of all the surfaces constitute the cylinder I. Now let us see, to access a data okay, how much time is needed, how much time can be needed. Okay, first thing is that after you know that which particular surface the data is, okay, that particular read write head has to be activated. Once that is activated, then you will have to move the head into, okay, that particular track, right? And once you have moved the head into that particular say track, then you will have to come to the particular sector either to read the data or to write the data into that sector. Okay, therefore, few things are involved here that you will have to first seek, so to say, by moving the read write head, the particular track or the particular cylinder and then the particular track where the data exists, and then you will have to wait for that particular data. So for example, if the data is here, then you have to, and the head is here, then you have to wait till this sector, after rotating a full circle almost, comes over to it. Okay, this is called the rotational latency, right? And you can immediately see, therefore, that the time to access a data into a disk is quite considerable. Okay, what are the times that will come to? I hope that gives a, I mean, more or less some picture of the disk drive unit. I'm talking, once more I said, I'm talking about the hard disk unit. You have used already floppy disk as say 3.5 inch floppy disk, which can contain 144 megabyte, 1.4 megabyte of information. This can contain huge information. Let us see some of the characteristics of this hard disk unit, right? Say the hard disk unit, a typical hard disk units parameters are the disk diameter is 3.5 inch, number of disk, that means number of platters, is around 10, and so the number of recording surfaces is around 20. Number of read write head per surface is 1. I was just talking of that mostly the type of disk we have, there is only one read write head which moves. It's possible that you keep a read write head for each of these track. Okay, for example, you can keep a read write head here, read write head here, read write head here for each of the track. Okay, but that is very costly and it's very seldom used, right? Therefore, the number of tracks, number of read write head per surface is 1. The number of tracks per surface is to the of the order of 6,000. Number of sectors per track is 150. It can vary. For example, since the outer tracks have more spaces, the outer tracks can have more sectors than the inner tracks. Okay, but I've just given an average figure of 150 around. Okay, typical figure, so to say. Storage capacity per track sector, you please mark, that is 512. Okay, half a kilobyte, right? Track recording density is 110,000 bits per inch. Okay, storage capacity per surface is 445 megabyte, and therefore you can see the storage capacity of the disk drive is around 9 GB here. Okay, disk rotation speed is 7,200 revolutions per minute. Average seek time is 7.9 millisecond. The seek time is, as I told you, that to find the track, okay, as the head assembly should move. Average rotational latency is 4.2 millisecond, okay, which means you can see that rotational latency, that if you have just missed the sector, then it has to come to the entire rotation before it can come to the under the disk under the read write head. Or it can be, if the read write head is here, if it's lucky, then the sector will immediately come under the read write head. Okay. Therefore, the average rotational latency is 4.2 millisecond, and data transfer rate, once the data has started coming into the read head, okay, is 20 to 40 megabit per second. Okay, 20 to 40 megabyte per second. Now, this is, so to say, some typical figures. Naturally, it will vary from disk assembly to disk assembly. Okay, and very huge disk spaces are available, right? Now, let us come to another kind of this, okay, which are very much in use today, that compact disk or CD-ROM. Let us in brief give the working principle of it. Okay, in the case of a CD-ROM, we have a laser source, some lenses, okay, that comes over to here. It's a parallel laser that comes. Okay, this is a light beam splitter. It goes straight with a mirror, it comes over to here, and this is in fact your CD-ROM disk surface, right? Basically, it is a plastic substrate on which, okay, you have, I say, this land and pit as they call it. That means there is depth and height. Okay, the depth is called the pit and the height is called the land. That is way the data is recorded. Okay, for example, that pit, the land may represent 1, the pit may represent 0. The laser beam gets reflected from here, and the reflection will depend upon whether the reflection is from the pit or from the land. Okay, and that is detected by means of optical transducer and the detecting circuit, and the data is generated. The sequential data or the serial data is generated from here. Okay, you can now have a system here which will parallelize this serial data that comes, and then the parallel data can be outputted. Therefore, you see that this is in brief, okay, and I should say the barest minimal way, I'm explaining the working principle of a CD-ROM, right? Now, the advantage of the CD-ROM is that it is very cheap, okay? Some of the characteristics of the CD-ROM that I am showing here, that the pits and lands is 0.1 micrometer wide, okay? Diameter of a CD-ROM is around 12 centimeter. Capacity is 600 megabyte, which means it can hold almost 240,000 pages of a printed text, okay, of the average size, right? Access time is 100 millisecond. Data transfer rate is 3.6 megabyte per second at a 24 speed one, okay? As you know that the speed varies, okay? Now it has turned out to be quite, at present, it's quite higher than 24. I think it's 32 or more than that, okay? The advantage, of course, is that it can be mass produced at very low cost by injection molding, okay? And therefore, the cost of a CD-ROM is very low, and it's therefore a very convenient way of mass storage, right? If you want to keep, so for example, that books, journals, okay, or other materials, okay, permanently, in that case, you can have the CD-ROM, transfer all this information from the CD-ROM, and for disseminations, for distribution, you can copy them and then distribute it at quite a cheap rate. Okay. Now, there is another that mass storage devices we have, which is magnetic tape. I am not discussing magnetic tape. It is more or less like that audio tape you have. It can be in the form of a cassette. The speed is really low, because you know that if the information is at the one end of a cassette and if you redirect it is at the other end, to find that information at the other end, a good amount of time is needed. Okay, these are the magnetic tapes are mainly used for, so to say, that backup storages, right? Now, this is the memory units that we are talking of, and these are the memory units we will be needing to use and we will be using in our future lectures, okay, including our discussions on operating systems, right? Now, just to summarize the informations that we have, okay, that say we can arrange that entire memories into memory hierarchies, right? First comes, the CPU registers, right? Then the memory, the static RAM on the dynamic RAM, the disk, and the MAC tape. The access types you can see here it is random, here it is random, here it is also random, okay, right? This is a direct access in the sense that if some informations in the disk is needed, okay, we can go to that particular sector and get the address, get the data. But here in the case of a tape, it is sequential. Access time you can see that varies from 1 to 3 nanosecond here, 5 to 25 nanosecond in the case of a static RAM, 60 to 120 nanosecond is the main memory, 10 to 20 millisecond in the case of a disk, okay, at 20 millisecond to 10 second in the case of a magnetic tape, right? Cost is also, at the same time, highest here and the lowest here is quite high. How much high depends upon exactly which CPU you are using. $100 to $200 here, $5 to $10 here, $0.1 to $0.2 in the case of a disk, and $0.02, okay, in the case of a tape. And the capacity is lowest here and the highest here, okay, as you can expect. It's 64 registers to say 1024 registers, a typical figure I am saying. Okay, naturally it's high cost. I'm assuming that it will be if you use a static RAM, say 256 kilobyte onwards, you will use. Main memory, okay, it can be from 16 megabyte onwards, as huge as you choose, almost nowadays. Disk capacity is from say 8 gigabyte to as huge as you choose, okay, and the tape in the case of a tape it can be 1 terabyte, okay. Now this is so to say that summarizes, right, the characteristics of the different memory devices, okay. Now that's all for today's discussion, and the next lecture we'll see how these different memories can be very fruitfully utilized so that you can try to have the benefit of the fastest memory unit and have the benefit of, okay, the mass storage of the largest memory unit. Thank you.